I'm going to proceed by introducing our speaker today. We have with us Professor Amin Rahimian, who is an assistant professor at the University of Pittsburgh with their Institute for Cyber Law, Policy, and Society and Security. He's actually coming from the field of industrial engineering, which I guess is a little bit different, a little bit of a different perspective than what we're used to hearing from, but I think you'll see a lot of ties between kind of the techniques that we've been kind of discussing both in your coursework, but also that have come up in seminar, including differential privacy and kind of how they intersect with kind of cyber physical systems. So I'll pass it off to you.
Thank you so much, Hannah. It's a great pleasure to be here and talk to you all. Let me know if you cannot hear me. I can maybe shout. Today I'm going to talk about privacy-aware sequential learning. It's a result that been developed by Yushin Liu, a final year PhD student at industrial engineering at the University of Pittsburgh, and we've been working together to think about the consequences of privacy to a model of sequential learning. So in that model, you can think about people who are arriving on a platform, or more broadly in a context of taking actions in a society. They each would arrive in a sequence, and then each individual has the observations that are private to themselves, and they also see what people before them have done, and they use these two pieces of evidence for making a decision at that point, and then they leave, and then someone else comes. So in that sense, it's called sequential learning. You can think about, for example, your decision to report a vaccination status to a vaccine registry. Your decision to take up a vaccine may have been influenced by your medical history, and you may worry about revealing information about that medical history. So that is where the privacy concern comes into play. But in general, your decision to take up a vaccine is not just based on your medical history or private information or your consulting evidence on that vaccine. You may also be influenced by people before you. So that's the sequential aspect of it. So people acting based on their information, their private information, and also basing their decisions not just on their private information, but on the action of people before them. So these two dimensions characterize the learning environment, the sequential learning environment. And in this work, we are interested in understanding consequences of privacy concerns to this learning environment. Before getting into the details of the privacy, let's spend some time to understanding what this sequential learning entails. Its history goes back to economics. In early 1990s, there was a number of works by Birchandani, Herschleifer, and Welch that pointed out a theory for explaining how herding can arise as a consequence of rational choice. So he was interested in what happens when people follow each other, and that herding can indicate inefficiency in society. So as a society, we all have access to a lot of information individually, but what happens that we follow an inefficient choice. So he was trying to explain fast fashion and herding as a rational choice. And a good example of making sense of it is you can consider there are two bakeries on two sides of the street, and the individuals have some signals about which bakery is the better one. Well, at some point, you may just see which one is more popular and follow that. So that following of the popular opinion or a popular choice can prevent further learning if at that point actions do not reveal signals anymore, and they are just based on people following each other. To basically model this as a rational choice, you can consider a situation when there is a binary state that can be an objective truth that can take two values, say -1 or +1, And you can also consider each of these agents having a signal that will also be binary, +1 or -1, and then they need to take an action, also binary. So if that action corresponds to the true state of the world, then they are taking a correct action. Otherwise, a wrong action. And the signals are informative about the state of the world. That is where the information comes into play. For example, in the case of a bakery, each person may have some signal about which of the two bakeries are the higher quality one. And that signal is not a it's not a certain signal, so there is decision making under uncertainty going on, in the sense that the signal that you have would agree with the state of the world with some probability greater than 1/2, but it's not always coinciding with the state of the world. The state of the world could be 1, and you observe a signal -1. So you have your signal gives you a belief about the state of the world, but that belief has uncertainty. When you think about the signal and you want to base your decision just on your private signal, you're only correct P% of the time. And P is the probability that the signal agrees with the state of the world. The hope is that by seeing each other, they can go beyond that P, that they can improve on what they can do alone. So that is the idea of social learning, that each of us have access to a piece of information, but as a society, we have access to more information as a whole, and we can learn from each other in a social learning scenario. So in this model, the first agent can receive a signal and then take an action. For the first agent, there is nothing to base the action on other than their private signal, so they will choose, say, the left or right side for the bakeries. So the rational action will always coincide with the private signal. The second agent has the first agent's action and can attribute it to their private signal, and they also have their own private signal. It may be tied, they may go with their own private signal, or it may be contradict, or if there's a majority and so their private signal agrees with what they saw from the agent before, then they will just follow that agent. So now we have two actions, and it could be that these two actions, they both coincide with each other. So now we have two people who have both chosen the left bakery. The third agent that comes into this sequence, having seen the first two agents, then no matter what private signal they see, there's always going to be a majority of -1. If they see -1, then there are 3 -1s. If they see a +1, then there are 2 -1 and 1 +1. So the majority is always -1. So the rational choice for the third agent is to always follow the herd. So that is how a herding can arise as an optimum choice for an agent in a sequence. And then from that point on, there's always going to be this majority that is hard to contract with any private signal. So learning basically stops here. People are just going to follow the majority. That's what we call an information cascade. So the purpose, so this observation, this model led to a large literature that tries to understand various aspects of social learning. A very simple setup: when agents arrive in a sequence, then they leave. They could persist, and also the observations do not need to be a complete observation setup. An agent in a sequence may only see a subset of agents before them. There are issues of the complexity of computing the actions in this model. The actions may follow a network structure. So all of these issues, whether the agents take actions repeatedly, whether the observation structure is following a network structure, a random subset of agents before them, they have led to a rich literature that studies various dimensions of social learning. But for us, we're interested in the issue of privacy. So how these learning outcomes that I described, for example, herding, would be affected when agents have a privacy concern when they are taking those actions. Before getting to the notion of privacy, there is another aspect of this model that I would like to point out. When I was talking about signal, like binary signals, the amount of information that the binary signal can reveal is fundamentally limited because of the discretization of the signal. But the signals can be richer. For example, a continuous signal like a Gaussian signals can lead to a different learning behavior, and they indeed do. So you can have a setup when you still have two states. One of them is objectively better than the other, binary states, and the signals, instead of being binary, they could be continuous. And then you still need to take action based on those binary signals. In this case, the continuity of signal would guarantee that eventually people are going to learn the truth, in the sense that if they form a Bayesian belief about the state of the world, then they can look at the sequence of observations before them and their private signal, and that Bayesian belief will converge to would converge to a point mass on the truth, meaning that they put more and more probability eventually on the correct state of the world. You can think about it as a hypothesis test, or like a classification from a more machine learning perspective. But this belief, this Bayesian belief, is going to converge to the true state, and the reason is because of the richness of the signals in this case. But still, that convergence can be slow, and so we can still think about the efficiency and the learning outcomes. But instead of thinking about whether people eventually take the correct action, we need to think about how fast that belief ratio that you put on the correct and false state, how fast that belief ratio converges to infinity. Because so it's one of them will go to 1, the other one will go to 0, but how fast? For example, a good baseline to have in mind is when there's an agent that has access to the private information of everybody up to that point. This is the optimum learning. This is basically a good benchmark to think about when you're thinking about the quality of learning, because part of the inefficiency of this sequential learning comes from the fact that you don't see the private signals of others, you see their actions, and you need to attribute that action to the private signal. And that limitation of how much actions are revealing about the private signals, that is one of the sources of inefficiency in sequential learning. So if you consider a benchmark when an agent has direct access to the private signals of everyone, then you can think about how fast the belief of that hypothetical agent will, the belief ratio of that hypothetical agent will go to infinity, and compare it with what you see in a sequential learning scenario and reason about the inefficiency. In this case, when an agent has access to the private information of everyone before them, that information accumulates through a law of large number. So each piece of information will, in expectation, contribute an expectation of the log belief ratio. So that expectation is the K divergence of the signals under the two states. So at each point, you're going to accumulate a piece of information. So the rate at which the log of this belief ratio is going to converge to plus infinity is going to be asymptotically n times the KL divergence of the distribution of the signals under the two states. In a Gaussian case, you can think about the signals as being distributed with mean equal to the state of the world. So if the state of the world is -1, then the signals have mean -1. If the state of the world is +1, then the signals have mean +1. And then the K divergence is going to be just a constants based on the distance between these two Gaussian distributions, and the benchmark would be n times that, the asymptotic rate at which the belief goes to infinity. Now this rate is going to be reduced to square root of log n, which is a much smaller number than n. So the one way to think about what goes wrong is that there could be these long times in which agents are falling into an information trap, and they are basically they have this false majority on -1. Say if Tuesday is +1, there's this long time that agents are falling into traps of taking -1, and they need to wait until an agent receives a strong enough signal that counteracts its majority. Because signals are continuous, their likelihood ratio is unbounded, this is guaranteed to happen eventually. So eventually someone comes into this sequence that has a strong enough signal that takes you out of that false majority, but how long you need to wait for that to occur can be very long. And that is what is causing this reduction from N, the benchmark of agent with direct access to private signals, the reduction from N to square root of log N. And so this rate at which the asymptotic belief converges to infinity is one measure of learning, the speed of learning, but there are other ways in which you can characterize the efficiency of sequential learning with continuous signals. One way is to measure how long you need to wait in expectation until someone takes a correct action, so expected time to the first correct action. And you can also look at how many wrong actions you take until there is a point at which everyone from that point onward will take the correct action. So time until the correct cascade. They end up being kind of equivalent to each other because there's a renewal aspect to this setup. But the thing is that under the non-private baseline for sequential learning with these continuous signals, both of these measures, expected time to the first correct action as well as the total number of incorrect actions, are going to be infinite. So in expectation, you may have to wait an infinite amount of time until someone takes the correct action in this sequential learning. So we're going to ask, how does privacy concerns for these agents that are arriving in a sequence affect these learning outcomes? In the binary case, they care about the probability of a correct cascade because we saw that it could be that the agents heard on a wrong action and they never get out of it. So then in that case, we want to see what is the probability of a cascading on the correct action. In the continuous case, the agents asymptotically are guaranteed to always take the correct action, but we would be interested in the rate at which that correct cascade arises, the speed with which that correct cascade arises, characterizing that speed with the ratio of beliefs as well as the expected time to the correct action or the expected number of false actions. So before going further into how privacy can shape these learning outcomes, let me pause here and ask if there are any questions that I can clarify about the sequential learning model and how we are thinking about the quality of learning outcomes in the sequential learning model. Because the remainder of the hour is going to be about how privacy changes these learning outcomes.
I was just wondering if you could clarify kind of the context of what types of, I guess, scenarios sequential learning you're talking about. Because I can imagine that there are things such as people expressing privacy preferences and making privacy decisions that actually probably don't converge on decisions, and there might not be kind of a majority of decisions. So I don't expect that is kind of what we're talking about here. But can you give an example of what type of decision-making scenario is applicable?
Right. So, perhaps a good example could be an online poll that you can see the actions of people before you. You also have an opinion about what you want to vote for. The question is, if the context of voting is very sensitive, then the vote that you leave in this online registry can reveal something about your private information, and this may imply misreporting or basically the idea of a vote would be that by people sequentially leaving their vote, eventually we would come up with a good consensus. But the privacy concerns that people have when they're leaving those votes can affect that good consensus. It can affect the quality of information aggregation. Similarly, in more like, for example, in health fads, whether following some procedure or eating something or drinking something else, is it good for you? Is it bad for you? You may base it on what other people think, but you may also have your own private information that would form your decision. And what you report to others would help people after you to also make a decision. But would that report be honest and truthful if this context is very privacy sensitive?
Exactly.
Thank you for the question. Yeah. Any other thing about how we think about the quality of learning in this sequential scenario that can help clarify? Okay, great. So, given this sequential model, we're going to ask how would agents make decisions subject to privacy concerns. So when they are, say, leaving a vote, they're going to worry about what that vote is revealing about their private information. That vote is going to be based on what they have seen in the sequence before themselves. It's also based on their private information. But now we have a privacy concern. And we saw that one of the main phenomena in sequential learning is the issue of information cascade, information trap. The fact that there are majorities that become sticky and it's hard to get out of. And that prevents the ability of agents or people who are arising later in the sequence to learn about private information of people before them, because most of the people before them have been just following the majority. So we can think about this as an information trap. But now, privacy can make this information trap less sticky because now actions are going to be less revealing about private signals, and the majority may be less reasonable to follow. So it could be that learning improves from that perspective. But it could also work the other way, in the sense that now actions are less informative about the signals, therefore agents learn less from each other. And that can hurt the quality of learning. So this question boils down to how is information cascades affected by the privacy concerns, and which of these two possibilities are going to be more dominant when we think about the quality of learning. It turns out the binary case and the continuous case will get to different type of results, and they're both are going to end up being somewhat surprising, that the privacy concern can actually improve the learning. So it's really the information trap aspect that is more or less dominant in the analysis, especially for the continuous signals. But to be able to point that out, we need rigorous ways of thinking through privacy-aware decision-making in this sequential scenario. So what does it mean for our agents to hide their private signals and at the same time take an action in a sequence? For that, we're going to use the formalism of differential privacy, which you have seen in one form or the other in different applications. Just as a reminder, you can there's a close relationship between privacy and this way of thinking and randomness or randomization in an algorithm design, or in this case in the choice of an action. It's because you want to prevent the possibility of attributing an observation deterministically and confidently to data or signals in this case. So you want to basically make that connection uncertain, so that an observer, it could be an adversary or it could be any observer who sees your action or the output of your algorithm, will have some uncertainty about the input and cannot. So that uncertainty is quantified by the privacy budget, and it's what prevents a privacy leak to some extent. If your privacy budget is very low, you can think about it as as a constraint on the design of your algorithm. So if your constraint is very strict or you have a very low budget for privacy to consume, then you really have no way of leaking information. So you're preventing information flow. You can think, in this case, we expect the learning to suffer. On the other hand, if your privacy budget is very high, then this differential privacy constraint is not really limiting your action in any meaningful way. So you're back to the non-private baselines. And we're able to investigate the effect of this privacy budget on the actions and the sequence of actions that are taken in a sequential learning scenario and investigate the learning outcomes. So the implications on learning outcomes. So I talked about continuous and binary actions. So with the continuous actions, I talked about continuous and binary signals. With the continuous signal, there is this challenge of how would you think about the implementation of differential privacy, or because typically when you're dealing with a data set, it is clear how you define the notion of adjacent data inputs to be able to prevent leaking information about whether your data is about that includes a role attributed to an individual or a human subject or a patient or not. So the removal of that row should not change the output of your algorithm too much. That is a typical situation when you would apply differential privacy, and it's clear how you would want the constraint to be applied. It is based on removal or addition or a change in the data entry. But when we have a continuous signal that we want to protect, that change is going to be, so we need to be a little bit more careful how we want to think about the information protection. So for the continuous signal, what we want to protect is the location of the signal. It could be a political leaning or some private opinion or some expression that would be the basis of your action, and you want to protect that to some extent so that your action is not completely revealing the location of the signal. For that, we use a variation of differential privacy called metric differential privacy. For signals that belong to a metric space, that e to the epsilon constraint is going to become looser and looser as the pair of signals that you have in mind as input to your algorithm go further and further from each other. So it's not just e to the epsilon, it's e to the epsilon times the distance between pairs of signals when you're thinking about how differential privacy constraints your output. That's the notion that we're going to apply when we are analyzing the continuous signals. In the binary signal, it is a simple case of just making sure that your binary action is going to be giving limited information about your binary input. So if you have come across randomized response, which is a very typical differential privacy mechanism, it would suffice for us for finding signals at that point. We would basically randomize each action for each binary action so that the binary signal is going to be limited to the output by e to the epsilon, the probability of each output under different signals. So these two are enough for us to rigorously investigate the privacy constraint in a sequential learning scenario. And we now have all the tools that we need to ask how would the quality of learning change in the binary case, in the continuous case with these privacy concerns. But before going to the analysis of the learning dynamic subject to these privacy constraints, is there anything that I can clarify about these privacy notions? For example, local differential privacy for binary signals and binary actions is just a typical randomized response, or the metric differential privacy that may be newer to you, or the differential privacy itself, how it's going to be applied here.
Am I correct in my understanding of metric differential privacy as sort of an extension of inferential privacy where rather than being just constrained to neighboring inputs, you can have any pair of inputs, but then the distance between them is also taken into effect. Is that a...
Yeah, exactly, yeah. That's a good way of thinking about it. Any other?
So when we think of different applications of differential privacy, the discussion is around the privacy versus utility trade-off. So I guess, again, I'm asking for examples here, and what context would a higher information flow and maybe kind of a reduced privacy budget be beneficial versus a kind of a higher information flow scenario, or sorry, the opposite, a higher privacy versus reduced information flow scenario?
Yeah, exactly. That's a very good question, and I actually at the heart of what makes this result kind of surprising and striking is that typically when you impose privacy, you expect to have to pay a cost for it. So we have a performance in the case of sequential learning. We care about the ability of individuals to improve their decision making so that as a society we learn. And we expect that by imposing privacy, that ability should suffer. What's striking and surprising under this model is that in the type of scenarios modeled by sequential learning, that's not necessarily true. So the privacy utility trade-off, the idea that by imposing privacy always your utility or the quality of learning should always suffer is not necessarily true. We have identified situations where privacy actually improves the ability of individuals to learn from each other because the privacy concern, although it limits the informativeness of actions about private signals, it also reduces the incentives for herding in a rational sequential learning scenario. And that second aspect actually ends up to be more dominant or completely dominant when we are analyzing continuous signals. And also, still interestingly, there's a non-monotone behavior that I'm going to describe in the binary signals too. Yeah, thank you for the question. Okay, so if you're happy with this information theoretic way of limiting how actions are going to leak information about private signals, then we can basically proceed with analyzing the rational choice subject to privacy constraints. So the agents are going to learn from each other, but as they take actions, they take into account the privacy implications of actions revealing their private signals. And this differential privacy randomization can reduce the informativeness of actions, but also reduce the stickiness of information traps. And our analysis can reveal the balance between these two. So we are ready to present the first setup in the privacy versus sequential learning. It's going to be in the binary model. So the mechanism or the strategy that the agent takes, given the history of actions that they have observed and the private signal. So agent -1 is the history of actions that agent has seen before them, and then Sn is the signal that agent N has. This would follow a randomized response scenario, meaning if your choice without privacy was +1, then you're going to flip a coin with probability 1/1 plus e to the epsilon. This is something that you would see in a typical binary setup for differential privacy. And then most of the time, if epsilon is say 2 or 3, most of the time you're going to take the same action, but sometimes you're going to take a different action. For example, report something else to a registry that is keeping track of votes or recording some other sensitive behavior. So the randomized responses strategy is going to satisfy the differential privacy constraint. But then the question is, how does it affect the learning outcome? The key to the analysis of the learning behavior or a learning dynamic under in the binary setup would be in the information cascade threshold. This is a threshold that determines how strong a majority should be for you to ignore your private signal. Because as soon as a rational agent ignores their private signal, they're going to follow the majority, and any agent after them is going to do the same thing, because the majority is only going to get stronger at that point. So the key to understanding this dynamic is to characterize how many signals I need in one way or the other for me to ignore my private signal and follow the majority. In the case of, in the non-private case, we saw that two would be enough, because as soon as there are two more of one signal than the other, then even if my private signal contradicts that majority, it's not enough for me to follow it. So I have to follow the majority at that point. So, but as you can imagine, this threshold is not going to be affected by the randomization. If anything, you would expect it to become higher or lower. Higher, right? Because when you impose the privacy concern, you would need more agents to take the same action before, because actions are less informative about private signals. So that is the sense in which majority becomes less sticky when you impose privacy concern. So two is no longer enough for you, depending on what the privacy budget or what the probability of randomization is. Two is no longer enough for you to ignore your private signal. You may need three people taking one action more than the other in the history for you to ignore your private signal. So what we can do to Markov chain analysis is to compute this information cascade threshold K, and to relate it to the privacy budget as well as the quality of the signals. So the probability that your signal agrees with the state of the board. You can imagine that in a situation when the quality of signals are very high, then agents are going to rely more on their private signals, and so how much the information cascade is affected is going to depend on not just the randomization, the privacy randomization, but also on the probability of the correct signal. So this result seems like a bit too much to digest in a slide, but there is a good way of visualizing what happens and how the learning outcome is going to depend on probability of the correct signal, the quality of the signal as well as the privacy budget. So what you can do is to plot the probability of a correct cascade. Remember, that's the notion that we have for quality of learning in the binary case, and plot it versus the privacy budget epsilon. So what you see here is these intervals that are shown by different colors. The first interval, if you think about it at a very high privacy budget, we are back to the non-private case. So that is what you see with the horizontal lines. And then these layers, they are just different signal accuracies. Yeah, it's not surprising that when the signal accuracy is very high, that this private signal are mostly agreeing with the state of the board, then the probability of correct cascade is just higher. So those top layers are corresponding to highly accurate signals, and then as you go below, you're getting less and less accurate signals. But that's just the property of your information environment. Some contexts are such that people get very accurate signals about the unknown. In other contexts, less accurate signals. So that aside, then there is this issue of how would the privacy budget affect the probability of correct cascade. So in all of these environments, you see there are these intervals over which the information cascade is fixed. So at the first interval, starting from high privacy budgets to a limiting value, you can think about that at like the left side of an interval. The information cascade threshold is equal to 2. So your information cascade threshold has not really increased by imposing those high privacy budgets. So at that point, the probability of correct cascade is just going to go down as you decrease the privacy budget, because there's no benefit of reducing the stickiness of information traps in that interval. This is starting from a very high privacy budget, and then I'm reducing the privacy budget until I reach the end of the red curve. But what happens when I reach the end of the red curve? There, now the privacy is so strict that 2 is no longer enough for people to follow the herd, to throw away their private signals. So information cascade threshold increases from 2 to 3. So that is where the non-monotonicity come into play. That there are going to be values of privacy budget where with more privacy, with more stricter privacy concerns, you actually get benefit of improved learning as well. And we will see that there's starker versions of this in the continuous signal, but even here with the binary signals, we already identify situations where stricter privacy concerns actually improves learning. And it could be that you are in a region of epsilon implied by the context that you deal with. So between those regions, there may be reason to reduce epsilon a little bit to improve learning, if that implies going from one interval to the next, like from red to the green, or from green to the blue or purple. So that's the gist of the analysis in the discrete case, in the binary case, and I'm happy to take questions on the binary setup before going to the continuous case.
Yeah, there was a question on Zoom. So the student is asking, kind of, like these properties seem kind of nice in this model. Have you seen this reflected in kind of real world phenomena as well? Maybe in things like social media trends or stock market behavior? Or how would you expect this model to apply to kind of real world decisions as well?
So I think one response variable, one outcome that I would try to look for is to try to think of situations where privacy has improved the quality of sequential learning. So so one can be so it's like one way of taking this result is from a normative or prescriptive perspective, that these results tells us how to design, or how should a rational agent behave, and what are the consequences of rationality. So that's one way of taking lessons out of this from a decision theoretic perspective. What you're asking is also a very important dimension, like from a descriptive perspective. What can we observe in the real world, and how would the real world coincide with this? And I would have to think, and I would be very interested to think more carefully about this and document evidence of cases in which imposition of privacy would improve social learning. Yeah. Yes, please.
Will the dimensionality of the data that you're processing or considering actually affect the information cascade threshold?
Here, our signals were binary. Actions were binary, and state of the world were binary. When you think about dimension of the data, you're thinking about signals instead of being binary to taking multiple values.
I was thinking that each value was binary, but then let's say it's a matrix instead of it being a singular value. So when that dimensionality increases, how would the information cascade be affected?
So it's it is. So instead of binary, for example, we can have a binomial signal. Then the dimension is n rather. So I mean, not to confuse it with the n that I'm using here for the order of the agent in the sequence. Let's say n. So then, and it could also be m could be large, and so in some sense, at some extreme, you may get to a continuous signal, right? A continuous signal, in that sense, is an extremely high-dimensional binomial signal. Like, for example, you can think about this as rather than you having a one piece of information, you have you run an experiment m times, and then you look at the average of the outcomes. Then that average of the outcomes, as the number of observations become larger and larger, it's going to converge to a Gaussian distribution by central limit theorem, right? So one way of thinking about the dimensionality and the effect of dimensionality of the data is to think about this distinction between binary and continuous. Of course, like figuring out the exact math in between is going to be pretty challenging, but I wouldn't be surprised that some of these the benefits, like the way that we see in the continuous case, learning speed is significantly faster is going to be true. So in that sense, I expect that with more refined private signals, we would get a sharper distinction between the non-private baseline and the private baseline as you increase your number of private observations, the dimensionality of your private observations, the resolution of the private observations. Yeah. These are very extreme cases, the binary and the continuous. Yeah, of course. Thank you for questions. There was maybe another question on the chat.
No, it's just a thank you.
Yeah, no, thank you so much for your questions. It's very helpful. So if there are no questions on the binary model, I think we're set up to go now to the last part of the talk, which is about the continuous signals. So yeah, I mean, thank you for the question. It's a good segue to think about. So now, what happens if rather than just having this coin flip as my private information, I have a real value with a lot of information to base my decision on. I still have people before me that have taken actions, and those actions would be part of why I make a decision, but I also have a real value to base my decision on. And we're just talking that we need a compatible notion of like a variation of differential privacy that helps us hide the location of that action, and that would be the metric differential privacy. So, with that equipped with that notion of differential privacy, let's think about how some of the simple implementations of privacy may look like. So, maybe you have come across global and local global sensitivity or sensitivity in general, and its relationship to differential privacy implementations. The idea is that when you want to design a differentially private algorithm, you would want to think about how sensitive the output of the algorithm is to the input signals, and then design your noise mechanism. It could be a Laplace mechanism, it could be exponential mechanism. However, you're designing your randomization, that randomization needs to be more noisy, or you need to randomize more and more the more sensitive your output is, because you want to hide how output depends on the input. So the more sensitive the output is to the input, you need more noise. If we take these vanilla or kind of typical ways of designing randomization mechanisms for differential privacy, we get a little bit stuck in the sense that the global sensitivity is going to be equal to 1 because the signals can be, so in the same way that we had information cascade in the binary case, in the continuous case, we will have a threshold on the signal. So if your signal at any point in time, there's a threshold. That threshold is determined by the history of the actions that you have observed. And if your private signal is below that threshold, you will take one action. And if it is above that threshold, you will take another action. It's a simple case of hypothesis testing. You're going to threshold your signal, and then you're going to take one action or the other. The thing is that with that threshold, if you want to talk about sensitivity, then your sensitivity is always going to be 1 because your pair of signals can be below that threshold or above that threshold, and then your actions is going to go from 0 to 1. And then what it means is that you end up always randomizing your actions no matter where you are, and there's no learning going on at that point. So that becomes a little bit troublesome implementation. And then you can think about the local sensitivity so that you only randomize your signal when we are really close to that threshold. But then there's the issue that your randomization algorithm, whether you randomize or not, is going to depend on where your signal is. And then just the act of randomizing would leak information. So that will not satisfy the definition of differential privacy if you just follow a local version of sensitivity that depends on the location of your signal. So that's where Yushin was able to come up with a randomization scheme that satisfies the constraint of metric differential privacy, and it's inspired by the randomized mechanism. It's a kind of a smooth version of randomized mechanism, and the probability of randomization goes down exponentially as the signal goes away from that threshold that I was talking about. So rather than like in the local case when you have something like a local sensitivity case, when you have some signals where you randomize and then that you don't randomize, that short edge is going to leak too much information, and then it will not satisfy the definition of differential privacy. But once you smooth that edge using like a design like this randomization scheme that you see here, then you're able to guarantee the metric differential privacy constraint on the one hand, and depending on the epsilon of differential privacy budget, and also it will not affect the asymptotic learning, because we would also satisfy the metric differential privacy with just pure randomization without the probability of randomization going on. And then the issue is that you're always going to randomize, and then there's no concept of learning at that point, asymptotic learning, that eventually agents are going to take a correct action. Well, with this way of randomizing, that you reduce the probability of randomization as you move away, as your signals move away from that threshold value, then you're able to, first of all, satisfy metric dimensional privacy, and also guarantee asymptotic learning, that eventually these agents who are following smooth randomized response are going to all take the correct action. So then we can ask, how is that learning dynamic now affected by the privacy, and how does it compare with the non-private baseline? Like, so in the continuous case, as you recall, as I was talking about at the beginning of the hour, in a continuous case, when we are guaranteed that the agents asymptotically learn, we care about how fast that learning occurs. Whether we need to wait a long time until the people cascade on the correct action, and so we will characterize this by the rate at which the belief goes to infinity the belief ratio. You can think about the posterior belief that an agent puts on one state divided by the other. The belief on one state goes to 1, the other goes to 0, so the belief ratio will go to infinity. We will characterize the log of this belief ratio, and that will give you an exponential rate and how fast this is. In the non-private baseline, we saw that the rate can be as low as square root of log n. With a fixed privacy budget, this rate increases to log n. So there is an square root of log n improvement to the non-private baseline. That is the result of the privacy randomization. So they learn asymptotically, and their belief converges to the point mass on the truth asymptotically much faster. And this improvement is not limited to the asymptotics. You can also look at the expected time that it takes for an agent to take the correct action, or the expected total number of incorrect actions. These are more non-asymptotic ways of thinking about the efficiency of learning in this setup. And in the non-private baseline, both of these measures are infinite, both of these expected values. In the subject to the privacy constraint with the smooth randomized response, as long as your privacy budget is less than 2 over sigma squared, sigma being the quality of the signal that they see. Low sigma means a very precise signal about the state of the world. A high sigma means a less informative signal. So as long as your privacy budget is small enough, these two measures are also guaranteed to be finite. So there are non-asymptotic ways in which the quality of learning is sharply improved. When we characterize these expected values, we also have a way of thinking about a value of epsilon that is best for everyone, like normatively optimum value of epsilon. If you're saying, if you set sigma, I think sigma here should be square root of 2, just so the range of epsilon for which we have convergences between 0 and 1, then you can think what value of epsilon minimizes the left-hand side, because, minimizes the right-hand side, because the right-hand side is in fact the expected number of incorrect actions. So you want people to take less incorrect action. And you will get a proportional number for also the expected time to take a correct action as well. So because these two end up being equivalent measures. So there is a value of epsilon that minimizes this right-hand side, and that value of epsilon, so say in a case of designing a privacy policy or a privacy mechanism for a platform, that can be very helpful to have a normative way of setting the value of epsilon. Or if you want to design a data release policy. Because oftentimes there is a question of how to set the value of epsilon. In this particular case, some value around 0.76 ends up to be normatively the best. It protects privacy, and it's the best possible for the quality of learning. So the final thing that I wanted to end the talk with is about the heterogeneity of the privacy budgets, because we're thinking about individuals in a sequence, and it could be that these agents are they come to the sequence with different privacy concerns. Some agents may be more or less concerned about revealing their information. So how would that heterogeneity affect the learning outcome? And so there's this behavioral reason to investigate heterogeneity of privacy, but there's also this additional dimension to it, that it seems that reducing privacy is improving the learning, and it's increasing the learning rate from square root of log n to log n. So the question is, how fast can we go? We know that there is the non-private baseline of n can be as fast as n. And changing this privacy budget, making it heterogeneous, is a way of getting at those bounds of learning in this scenario. So by allowing the privacy budget to be between uniformly distributed between 0 and 1, we can improve the rate all the way to square root of n. So not as fast as the n baseline for an omniscient agent that has direct access to the private observations. But quite fast when you think about the square root of log n, which is the rate that we had for the non-private baseline for the rate of asymptotic rate of sequential damage. And this rate is basically is an upper bound, so we cannot be better than the square root of log n with other privacy budgets, and we're always guaranteed to be greater than log n as well. So those lower and upper bounds are achieved. The lower bound is achieved by a fixed privacy budget, and the upper bound by allowing this heterogeneous privacy budget and the existence of agents that can take very small privacy budgets somewhere in the sequence. So as long as you have a way of incorporating those agents in your sequence, your learning rate is guaranteed to go way to the upper bound rate of the square root of n. So these are basically the gist of the results, and we can get this, similar results for the expected number of so like the two non-asymptotic modes with the heterogeneous rate as well. The two non-asymptotic measures of efficiency of learning. So they remain similarly finite under heterogeneous privacy budget. And so how am I doing in terms of time?
We just have a couple of more minutes left.
Okay, yeah, and I'm almost done with what I wanted to basically describe. This is a simulation that shows the log of the belief ratio, and you can see with different values of epsilon, low, medium, or high privacy budget, the log of the belief ratio can be at the rate at which it goes to infinity can be higher at lower values of epsilon, and especially compared with the non-private baseline that you see as a black line here. The randomness is kind of the simulation of the actions of the agents. So yeah, this is basically, and that is Yushin that's presenting the work on the information traps a few months ago. But yeah, so now the work has been the analysis by him. Yeah, so if we want to wrap it up, I think we go back to those first two issues, the information trap as well as the reducing the informativeness of actions about signals and how the interplay of these two lead to different learning outcomes in the binary and continuous case. Yeah, I'm happy to take more questions, especially about the continuous setup. I think I went through it a bit faster, but yeah. Thank you for your attention.
Unfortunately, we are out of time. I see students kind of peeking in from the next class. So I will have students who have additional questions follow up with you directly.
Of course, I will take any questions.
And thank you so much for coming in. I know it's not fun traveling in the rain, but
My pleasure. Thank you so much.